And in our probability unit, we use tree diagrams in the beginning, and we're going to tie our tree diagrams in to figuring out the addition rule, the multiplication rule, all those rules of probability that you probably never understood. You will understand when we do it here. You know, when you hit it in Algebra 2, we hit it so lightly. And, you know, you just say, what's the probability of this? What's the combination? What's the permutation? What's this? What's that? And it's very, very quick. In this course, we use it more. And the ones that you use with Bernoulli's, with the C thing, it'll actually make more sense when we do it here. So hopefully these will be things that you'll catch. These are your vocabulary. They're on your vocabulary list as well. So just to talk a little bit about your basic probabilities. A probability experiment is an action or trial through which specific results are obtained. I roll my dice. I flip a coin. Okay? I shoot the darts. Whatever you're doing to obtain specific results, how many heads do I get? How many bullseyes did I get? How many tails do I get? These are your probability experiments. Your probabilities, therefore, cannot change. Because if you're doing an experiment, that's the one thing you have to control is your probability of something occurring. Now, you probably remember your theoretical and your empirical. For instance, if you flip a coin, the probability of heads is what? 50%. So does that mean if everybody flipped 6 coins that they would get 3 heads, 3 tails?
No.
No. Theoretically, it's 50%, 1/2. Empirical, experimentally, this is your experiment to flip the coin 6 times, does not mean you will get 1/2, 1/2 all the time. Some kids might get 6 heads, 6 tails, 3 of each, 2 and 4, different amounts. That's your empirical part, your experiment. That's what you were trying to see. How many heads did you get? If we put all your results together, that's called the law of large numbers. The more times we do this, the closer we get to the theoretical probability. So that's where your law of large number comes in. When you run your experiment, the results of a single trial is called an outcome. So you'll have various outcomes from doing this. All the possible outcomes are listed in a sample space. These are all on your vocab, so start filling them in as you go. An event consists of one or more outcomes and is a subset of your sample space. A simple event is an event that results in a single outcome. I flip a coin, I can only get a heads. If I flip a coin and roll a dice, that's not a single event. Okay? Now, tree diagrams. Tree diagrams are really, really helpful in figuring out your sample space. Okay? Tree diagrams get a little cumbersome if you're doing this a certain amount of times, or you're doing a certain amount of things at the same time, flipping a coin, rolling a dice, doing something else. That becomes a little bit cumbersome, but your basic probabilities can always be found by a tree diagram. What this does, though, is find you your theoretical. This finds you your theoretical probabilities. Your theoretical probabilities are what should happen when I do this. Doesn't necessarily mean it will happen when you do this. That's your experimental one. So theoretically, when you flip a coin 3 times, you should get the sample space. So this is how you start your tree diagram. I always start with me. I'm going to flip a coin. I start like this. And this is why. This is me. I'm on a diet. This is me. The easiest way to do this is start with you, because otherwise kids get 3 trees. You have to have a, you know, your tree has a trunk to it, and then it branches out. So you have to have something that they all originate from. So start with you. You're going to flip this coin 3 times. First time you flip, what can happen on your coin? What can you get? Heads or tails. Now this probability doesn't change. This is 1/2, 1/2.
Okay.
This is coming back to you, right? Well, we start small, but we apply this. You wouldn't believe how many kids cannot make a trade for flipping a coin. It is a difficult concept. Now, after the first flip, you had a heads. You flip it the second time. What can you get? Heads or tails. So if you had a tails, you flip it again. Each time, this probability doesn't change. It's 1/2. Now you go flip it a third time. So the same thing can happen, heads or tails. And each time you do this, you have a 1/2 probability of getting a heads, 1/2 of getting a tails. Okay? If you flip this coin 3 times, and each time you had 2 possible outcomes, 3 times 2, here's your counting principle, should give you 6 outcomes altogether. Here's your outcomes. 1, 2, 3, 4, 5, 6, 7, 8. 2. Oops. Something happened here.
Oh,
Do you count?
4
4 out.
Everything's
Nope.
a lie to me now.
I flipped it 3 times.
My life is a lie.
Okay, take this off. Yeah, your life
What
is
is happening?
messed up now, right? Okay, so let's take a look at this. To get your sample space, we'll go back to that. It's actually 2 to the 3rd, but I don't want to go 2 to the 3rd right now.
Wait, so what you did is correct or incorrect?
Well, it's actually 2 to the 3rd.
Correct.
This is correct. But let's go through that, and this is 2, 2, 2, 3 times, 2 to the 3rd. Okay, but you don't have to do that part. You can count this part. Let's make your sample space. Here's where your sample space comes in. So we say you could get a heads, heads, and heads. Heads, heads, and a tail. Follow your branches. Heads, tails, and a heads. Heads, tails, and a tail. It seems simple, but this concept applies to everything. And it's easiest to see it on a coin toss. Next, if you skip branches, make another line on your chart. It's easier. Tails, heads, heads. Tails, heads, tails. I'm just following your branches. Tails, tails, heads. And tails, tails, tails. Here's your sample space. You have 8 things that can happen. Each one of these, because it's 8 things, has a 1/8 chance of happening. Now watch. 1/2 times 1/2 times 1/2 is 1/8. So this is 1/8 right here. 1/2 times 1/2 times 1/2 is 1/8. Each one of these has a 1/8 chance of happening. Your tree and your probabilities all tie in. Together, they have to equal 1. Now, once you do your sample space, all your probabilities come off of that. What is the probability of getting 2 heads and 1 tail? First of all, how many possible outcomes are there? 8. There's your bottom number. How many have 2 heads and 1 tail in any order? 3. There's your probability. Or, come through here. 2 heads and a tail. 2 heads and a tail. There's 1. Taking it off this is a little harder. There's 2. And there's 3. So it's a little harder to take it off your tree. It's much easier to go from your sample space. What's the probability of getting all the same? 2 over 8. Because you can either get what?
3 heads, 2 tails.
2 all heads, all tails. Isn't it more obvious from your sample space than it is from your tree diagram? Much more obvious. So I've got to, and you can reduce this, Don't reduce your probabilities until the very end, because what happens is if you're going to have to add them up, you're going to need a common denominator. I could say that what's the probability of getting 3 heads or 3 tails? I could ask it like this. 3 heads is 1 out of 8. 3 tails is 1 out of 8. Or says add them. I could ask it like this. Okay, so you got a number of ways to work off of your sample space. The sample space really, really is helpful. This concept of 2 choices works for having like children, boy or girl. What's the probability if I have 5 kids that they're all boys? What's the probability that I get 3 girls, 2 boys? This chart works the same way because there's only 2 choices. If I was flipping a coin and I have to do this 10 times. I have 9 heads in a row. What's the probability of getting the heads on the 10th flip?
I don't know, I'm pretty lucky.
1/2. Still 1/2. The probability doesn't change. You might get lucky, like Joe said. Joe's been pretty lucky so far getting all heads. But the probability is
Joe's
still...
pretty good.
All right, guys. you got to be grown up about this. Okay. Get your minds out of the gutter and let's be grown
I
up.
was only talking about the coins.
Okay.
Sorry.
Now the thing with this is, that's called like the fool's gold type thing. When people do the roulette wheels at the casinos, they think because red keeps coming out that the next one's going to be red. It's still a probability of 1/2 between red and black. But that's like the luck of the draw there. It's the luck part that comes in. But the probabilities themselves don't change. Sometimes you'll see an example in the book that uses a weighted coin. They'll use a weighted coin. You can have a probability of getting a heads 1/4, getting a tails 3/4. And they'll tell you that it's weighted.
How do they like shake dice or load the dice? Or...
I have no clue. They probably make one heavier than the other. There'd probably be something inside of it. They probably make one heavier. Okay, everybody can do a tree? All right, let's see.
I'm really good at drawing trees.
Okay,
Hi, Joseph.
here we go.
Take care, buddy.
Come on, guys. All right, we're going to find...
Wait, you just signed up for it.
Guys, turn up to page 119. You listening? Page 119. We're going to do a... Page 119. For each probability experiment, identify the sample space. A probability experiment consists of recording a response to the survey at the left and the gender of the respondent. A probability consists of recording a response to the survey at the left and the political party. Okay, so we're going to do this, and we're going to do at the left and the gender. What choices are there at the left? Guys, what choices are there at the left? Look at this, agree, disagree, no opinion. So, how do I get this started? I need to do a sample tree on combining these 2 things. What is the probability that I'll have no opinion and be a male? What is the probability that I'll agree and be a female? So I need to figure this out. So I start with me. And how many choices do you have in the survey? 3. So I have 3 choices to make. What can they be? Agree, disagree, no opinion. What's the probability of each one happening? 1/3. There's 3 possibilities. 1/3. Then I want to check the gender. What can you be for gender? Male or female? So, male, female, male, female. Okay, what's the probability of a male or a female? 1/2. Well, no, just a male or a female.
1/3.
No, 1/2. If you're not a male, you're a female, right? Are we doing all the same thing back there, guys? Okay, good. All right, so now, how many outcomes outcomes are you going to have for this thing?
Six.
How many outcomes?
Six.
1, 2, 3, 4, 5, 6. 6 things. 3 things times 2, 6 things. So watch what's going to happen. Here's my sample space. I agree, and I'm a male. I agree, and I'm a female. I disagree, and I'm a male. I disagree, and I'm a female. I have no opinion, I'm a male. I have no opinion, I'm a female. So now, what is the probability of being a male and disagreeing?
1 out of 6.
1 out of 6. What is the probability of just disagreeing?
2 out of 6.
2 out of 6.
1/3 if you like.
What is the probability of not disagreeing? 4 out of 6. There's your complement case. Good.
Q.
There's your complement. If it's not this, then it's everything else, right? That's the 1 minus. That's your complement case. Good. All this should take off your sample space. Sound good?
Good.
Okay, now you're going to try the next one. You're going to try number 2. A probability experiment consists of reporting to the survey, here's your 3 things, and belonging to one of the political parties, Democrat, Republican, or other. I want to see your tree, and I want to see your sample space. I'm sorry? Oh, no. You're just doing it now. I'm going to walk around with you. You're doing part 2 to try it yourself, number 1. You're making a tree. Part 2. Nope. But you belong to a political party.